Ever wondered how we can power entire cities without blanketing the sky in smog? The answer might surprise you, and it's hiding in plain sight, inside some of the most advanced structures ever built. Forget what you've seen in sci-fi movies. We're talking about modern nuclear reactors, the unsung heroes of clean energy. Today, we're going on an exclusive tour inside the heart of a nuclear power plant to uncover the secrets of how they turn tiny atoms into immense, clean power for millions. How does a fuel pellet the size of a gummy bear produce as much energy as a ton of coal? Stick around, because we're about to demystify one of the most powerful and misunderstood technologies on Earth. So let's start with the absolute basics. At the core of every nuclear reactor is a process called nuclear fission. Imagine an incredibly tiny superpacked ball of energy that's an atom's nucleus, specifically a uranium-235 atom. What scientists figured out is that if you shoot a tiny particle called a neutron at this nucleus, it becomes unstable and splits apart. But here's the magic. When it splits, it releases a tremendous amount of energy in the form of heat, and it also releases more neutrons. These new neutrons then fly off and strike other uranium atoms, causing them to split, which releases even more heat and more neutrons, and so on. This creates a self-sustaining chain reaction. It's like the ultimate domino effect, but instead of plastic tiles falling, it's atoms releasing pure energy. Now, an uncontrolled chain reaction is, well, not something you want. That's where the genius of a modern reactor comes in. Inside the reactor core, where all this action happens, are the fuel rods. These are long metal tubes packed with those small ceramic uranium pellets. Interspersed among these fuel rods are control rods. Think of them as the brakes of the system. They are made of materials like boron or cadmium that are fantastic at absorbing neutrons. By raising or lowering these control rods, operators can precisely manage the speed of the chain reaction. If they need more power, they pull the rods out a little, allowing more neutrons to fly around. If they need to slow things down or shut down the reactor, they insert the rods fully, soaking up the neutrons and stopping the fission process almost instantly. It's an elegant dance of physics, all happening safely within a sealed steel reactor vessel. Okay, so we've got this immense heat being generated from fission. What's next? This is where a nuclear power plant starts to look surprisingly similar to a traditional power plant, like one that burns coal or natural gas. All that heat is used to do one simple thing: boil water. In the most common type of reactor, a pressurized water reactor, or PWR, the water heated by the reactor core gets incredibly hot, over 300 degrees Celsius, but it doesn't boil. Why? Because it's kept under extremely high pressure, about 155 times the normal atmospheric pressure. This superheated high-pressure water is then pumped through thousands of tubes inside a massive piece of equipment called a steam generator. Inside the steam generator, a whole separate loop of water is flowing around the outside of those hot tubes. This secondary water absorbs the heat, and because it's at a lower pressure, it instantly flashes into high-pressure steam. So, to be clear, the water that was in the reactor core never mixes with the water that becomes steam. It's a closed loop, ensuring that no radioactive materials from the core can escape into the rest of the plant. This clean, powerful steam is the key to making electricity. It's channeled through massive pipes, ready to do some serious work. And that work happens in the turbine hall. This is where you see the real muscle of the power plant. The high-pressure steam we just created is blasted against a series of giant fan-like blades on a turbine, causing it to spin at incredible speeds, often thousands of revolutions per minute. This turbine is connected by a long shaft to a generator. And the generator is essentially a huge collection of magnets and copper coils. As the turbine spins the shaft, it spins the magnets inside the coils, creating a powerful magnetic field that pushes electrons around, generating a massive electrical current. And just like that, the energy from a split atom has been converted into the electricity that powers your home, your phone, and everything in between. But the story doesn't end there. What happens to all that steam after it has pushed the turbine? It can't just be released. For efficiency, it needs to be turned back into water and sent back to the steam generator to be boiled all over again. This is where those iconic giant cooling towers come into play. A third loop of water, often drawn from a nearby river, lake, or ocean, is used as a coolant. This cooling water flows through pipes in a condenser, where the spent steam from the turbine passes over it. The steam cools down, condenses back into water, and is pumped back to the steam generator to repeat its journey. The now warm cooling water is then sent to the cooling tower, where it's trickled down, releasing its heat into the air as harmless water vapor. That zests the steam you see coming out of the towers. Now, let's talk about the big question. Safety. Modern reactors are worlds apart from their early predecessors. They are built with multiple layers of redundant safety systems. The entire reactor core is housed within a massive, thick steel pressure vessel. This vessel is then enclosed within a primary containment building, a huge structure with steel-reinforced concrete walls several feet thick, designed to withstand incredible pressures, impacts, and even earthquakes. On top of that, passive safety systems are now the gold standard. These are systems that work automatically using natural forces like gravity and convection, without needing electricity or human intervention, to cool the reactor down in an emergency. It's a belt, suspenders, and another belt approach to safety. And what about the waste? This is another huge area of innovation. The spent fuel from a reactor is actually still about 95% usable uranium. Advanced and next-generation reactors, like breeder reactors or molten salt reactors, are being designed to run on this spent fuel, essentially recycling it to extract even more energy. This dramatically reduces the volume and long-term radioactivity of the final waste. The ultimate goal is a closed fuel cycle, where we recycle the fuel until only a tiny amount of waste remains, which can then be safely stored deep underground in stable geological formations. This isn't science fiction. These technologies are being developed and tested right now. So from a tiny atom splitting apart to the electricity powering our modern world, the journey is a marvel of engineering and physics. Modern nuclear reactors are a powerful tool in our fight against climate change, providing a constant, reliable source of clean energy 24/7, regardless of whether the sun is shining or the wind is blowing. It's a technology that has evolved immensely, prioritizing safety and efficiency above all else. The next time you flip a light switch, take a moment to think about the incredible journey that electricity might have taken, a journey that could have started with the simple, clean, and powerful process of nuclear fission. Thanks for joining us on this deep dive into the world of nuclear energy. If you found this fascinating, make sure to hit that like button, subscribe for more content, and ring that notification bell. Let us know in the comments what other technologies you'd like us to explore. Until next time, stay curious,